All right, so thank you for having me for this great opportunity. So I'm Eric Jung. I'm an assistant professor of material science and engineering. I'm also affiliated with the Nanoscience and Technical Center and then electrical and computer engineering. All right, so just a little bit of background on myself and then my lab members. So I studied at Seoul National University, UIUC, and I got my PhD from UPenn, and I also studied at Yale University. So all degrees from material science and engineering. So I joined the UCF as assistant professor in 2016. So I've been here for about 4 years. Whereas over the last 4 to 5 years, I've been, mentoring several postdocs, several graduate students, and dozens of undergrad students. So here the red boxed ones represent the current lab members. Okay. So many of my, former postdocs and this, students actually, move on to the industry such as Intel and also academia. I do have a couple of postdocs working at Yale University, and then some students at Carnegie Mellon University, and some at the national labs such as these. All right, so teaching activity wise, I've been teaching some material science course as well as the nano course. All right, so most of them are graduate level course. So I'm the one who actually got the CECS graduate teaching award in this 2002. All right. So many of my students actually, racked up, a lot of awards, recognition of their excellent research. So this is a short list of them. Okay. All right. So regarding my research activities, so since I joined the UCF in 2016, I have published about 50 papers, with UCF affiliation, right? And many of these papers, published at the UCF has been cited, over 3,000 times so far. And, these papers have been, in high impact journals in my field, such as Nanoletter and Nature Communication, things like that. Okay, so some cover images from my UCF works, and then my research has been supported by NSF, EPA, and Air Force Research, and so on. All right, so what do we do? Okay, for my research, I'm a material scientist, and my specialty is on nanoscale material. So basically, I study nanomaterials, so I developed the new nanoscale materials, and then studied their interesting material properties. So many of the nanoscale material actually gives out the unusual material properties which are unattainable in conventional materials. So we dig up the new material properties and then try to understand the fundamental behind the structure property relationship at the nanoscale, and then try to translate these useful material properties to the new cutting edge transformative technologies. All right. So material systems of particular interest at this point are two-dimensional materials, near atom scale, two-dimensional material. So what we believe, in carrying out our research is that, okay, so we bring out new materials and then we are able to realize, new opportunities, which has been, foreseen to be impossible with any conventional approaches. All right, so speaking of the two-dimensional material, so graphene must be one of the best known example for the two-dimensional material, right? Which we are all familiar with, right? So, okay, so the library of this two-dimensional material has expanded nowadays, and then, for now, we are actually looking at, other types of two-dimensional material as well, such as metallic, semi-metallic material as well as semiconducting material. So my lab, at this point, is particularly interested in digging up the semiconducting and metallic two-dimensional materials. And one of the material systems that we are presently working on is called 2D transition metal die technology, 2D TMDs. So 2D TMDs are materials, a compound material in the form of the MX2, so M means transition metal, and then X means the chalcogen element, all right? So by playing with the elements for M and X, we are able to realize various carrier transports from metallic, semi-metallic, as well as the semiconductor material. All right, so opportunity-wise, I mean, here what you're looking at is some diagrams show the property of the 2D materials compared to other materials. So many of these 2D TMDs materials are excellent in terms of electrical properties. What I mean is, mobility-wise, I mean, these 2D materials actually quite competitive with conventional silicon or, the 3-5 compound material, right? And also some of the 2D materials actually present a high on-off ratio, which is really essential for the, excellent digital electronics. At the same time, these 2D materials actually gives a large strain limit. So what it means is, so these materials can be stretched out almost like more than 10 times compared to the conventional, silicon or compound materials of the comparable thickness. So we look at these opportunities and then we strive to realize these excellent material properties for the new technologies, not only limited to the electronics, but beyond the electronics, such as energy and environmental technologies. All right, so this is landscape of 2D material research in my lab. So we grow 2D materials for which we do the chemical vapor deposition (CVD) process. So we do CVD process and then grow wafer scale 2D materials with various carrier transfer properties, semiconducting to the metal. We also do the atomic scale characterization. So what it means is, okay, so we try to understand the structural property relationship at the ultimate size limit. So here what you're looking at is the cross-sectional TEM view of the two different 2D materials. So, moly sulfide and the tungsten sulfide, two different 2D materials that vertically stacked up, right? So here what you're seeing is, I mean, individual atomic layer of, one of these 2D materials, the scale by is 1 nanometer. So what you're looking at is really tiny, feature, okay? So we do the growth, we do the characterization, and then we can integrate the developed 2D materials on unconventional substrates, such as paper, rubber, things like that. So that way we can actually realize unconventional, unprecedented material functionality, right? So at the end, we also do the device application, I mean, wide range of electronics, optoelectronics, and then environment, so on. All right, so speaking of the opportunity, I'll say the biggest opportunity from the 2D materials are in that they can be integrated on conventional substrate. So what I mean is, when we actually grow 2D materials, we grow them on rigid, robust substrates, which can survive high temperature chemical vapor deposition process, right? But in a way to realize their true potential, we have to, integrate these individual 2D materials on unconventional substrates, right? So unconventional substrate means it could be arbitrary substances, which can be bendable, stretchable, twistable, so on, right? So here we integrate 2D materials or any carrier type, semiconducting, metallic, so on, right? And then, so this, this approach is actually overcoming the, limitation of the conventional thin film growth technology, which is actually limited to the lattice match with restriction in terms of material assembly. All right. All right. So here, what I'm going to show is, okay, so this is a video that shows that, okay, 2D materials already grown on top of the growth substrate. And then now we immerse the sample in water, we can easily delaminate the, the only 2D material. All right, so 2D materials, okay, so this is indeed near atom thickness material. Okay, so for which we already kind of done some, surface treatment, things like this, so that way, we can easily delaminate and transfer whatever 2D materials onto whatever desired substrate. Okay. All right, so our vision and goals. Okay, so 2D materials are not only about size reduction. As I said, okay, so we like to, pursue their new opportunities for, transformative, technologies. So particularly, we are interested in realizing devices beyond the mechanically rigid, conventional silicon-based system. All right, so yeah, so I do have a couple of the slides to showcase my ongoing research. All right, so we can treat the individual 2D material as kind of paper, right? So what I mean is, okay, here you are looking at the individual papers, and then we can actually convert this two-dimensional paper into the three-dimensional object, right? You can do the exact same thing with 2D atomic scale electronic materials, right? So for which we developed the technique which is called kirigami patterning. So here is your paper, and then we do some patterning, like by using scissors. For the actual research, we use some laser patterning. We can create the three-dimensional device building blocks. All right. So what I mean is we can convert the two-dimensional material into three-dimensional form by which we can actually incorporate the novel functionalities. All right. So in terms of functionality here, what you're looking at is, okay, so I gotta play another video. So 2D material is already integrated on top of the this thing, right? And then as you can see, we can stretch it out in multifunctional manner, X, Y, Z direction, right? So by doing this stretching, we can preserve the the intrinsic material property of 2D material. So here what you can see is, okay, this is the IV curve, right? So intrinsic electrical conductivity of 2D material is well preserved, even up to 2,000 the percent stretching, right? We can also realize that some stretchable photo detection, right? So what it means is, the device can function even on the the large lateral stretching up to 100%, right? And then we still can detect the the light from the the source. All right. So this work has been published in Nano Letter, and then make the cover feature. All right, so okay, the extension of this kirigami, the based approach, we are able to develop some, small devices such as skin attachable heaters, as well as stretchable transistors. So here, what you're looking at is, okay, so this is, the transistor FET, which you can reversibly stretch between 0% and 200%. So throughout this stretching, you can see that device characteristics, P-type characteristics is well maintained. Okay. All right, so here's another opportunity. So we are working on 2D materials, and then now we are able to integrate 2D materials onto whatever substances. So we can integrate 2D materials on biodegradable, the dissolvable substances such as cellulose paper, right? So here's one example, right? And then we can integrate, the more sophisticated devices based on these 2D materials on top of this paper substrate, right? So advantage-wise, okay, so the main advantage is to replace the conventional, the silicon-based wafer, which actually turns out to be electronic waste upon the discarded, right? At the same time, as you can see, these entire device building blocks can be easily dissolved in some solvent, right? So which means, in principle, it is possible that we can develop the new device which can disappear, completely disappear once completing their targeted functionality. So this kind of very attractive in terms of the developing some device which demand the high level of security. All right, so speaking of the opportunity, collaboration opportunity. So I do have, several collaborations, within UCF and beyond the UCF, right? So within UCF, I've been working with, okay, so I just showcase a couple of them. Okay, so I've been working with, Professor Tanya Roy, MSc department, and then we've been working on 2D material-based, the AI computing technologies, so particularly, we are working on developing neuromorphic, the devices, all right?
Please wrap up, sir.
All right, so yeah, so in terms of environment, we are also collaborating with the Dr. Woo-Young Lee, and then we are doing the water desalination, and then in terms of energy, so I've been collaborating with the Professor Yang, and then we are working on making new catalysts. All right, so we also I also do have some external collaborator beyond the UCF. All right, so in terms of the future collaboration opportunities, so we are open to any types of collaboration with those who might be interested in using our two-dimensional materials. All right, so that's all for I have, and then I'll be happy to take any questions.